Oh, hello everybody. It's me, Miss Thibodeau. No, I'm just joshing you. I'm some other guy. I'm Mr. Athide. I teach math, and I'm subbing in this video lesson to teach you all about powers. And we're not talking about like invisibility or super strength, but rather math, the best superpower of all. This is a power. And a power has very specific features about it. When we refer to aspects of these powers, we do have to be very clear with the terminology we use. So this whole entire thing with this number and then a smaller thing written as its kind of hat, that whole thing is a power. And the power has two components. There's this component that looks like an A, and there's this component that looks like a B. This A, that is referred to as the base of the power. And written a little higher and a little smaller, just up to the right, is the exponent. Together, the base and the exponent make up the whole power. Now, just as multiplication is a shorthand way of writing repeated addition, powers give us a shorthand way of writing repeated multiplication. The exponent tells us how many times the base is a factor in whatever number we're working with. So 2 to the 1, for example, is just equal to 2. 2 is in there one time. If we look at 2 to the power of 2, that says that this base of 2 is a factor 2 times. So there it is once, and there it is twice. And when we say factor, factors refer to multiplication. Hence, we have multiplication between those two. When we have something like 2 to the power of 3, that tells us that the base of 2 is a factor in whatever number we're working with 3 times. So there it is once, twice, thrice. And that is the expanded form or the repeated multiplication form of 2 to the power of 3. And once we've written it in that form, we might be able to see what it's equal to, because 2 times 2 is 4, and then that times 2 is the 8 we've got there. There are some examples here. The task is to write these 3 as repeated multiplication. Take 63 seconds to pause this video and try those out now. Excellent. You tried them out. Let's see what you got. And if it compares to this. 5 to the power of 3 is equal to 5 times 5 times 5. It's in there once, twice, thrice. 10 to the power of 4 is equal to 10 times 10 times 10 times 10. So it's in there 1, 2, 3, 4 times. Finally, we've got y to the power of 5. Y to the power of 5 is equal to y times y times y times y times y. And note we can use these different symbols for multiplication. There's the cross product looking one, but also the dot. If you want, you can also represent this as, in brackets, a y times a y times a y times a y times a y. Because if there's no operation put in between a couple sets of brackets, the implicit operation is multiplication. Take another quick moment, give you only 45 seconds for this one, but see if you can express these two expressions as each a single power. Start now. I know I didn't say pause the video, but I hope you pause the video and you're resuming now, because I'm about to put some answers up in this business. Here we've got this 3 in here, so 3 is the base. So this is equal to 3, and we're going to put some exponent up here. For that, we just need to count how many times 3 is a factor. I've got 1, 2, 3. I know how to write a 3. 3, 4, 5, 6, 7 times. So this is 3 to the power of 7. And the other one, the thing that's being repeated is y. So this is going to be equal to y to the power of something. Question is, what goes in that something? That's how many times y is repeated. And I've got 1, 2, 3, 4 times. So this is y to the power of 4. Now, how we use brackets and powers is very important. An exponent always applies to what is immediately to the left of it, because there might be multiple things to the left of it, but only what is immediately attached to it, that's what it applies to. When we look at this, this says -2 to the power of 4. Said out loud like that, it doesn't really make it clear what's going on. Written like this, we can see that this 4 applies to whatever is in this bracket. That's what it's immediately to the left of it. And that bracket pairs with this other bracket. So worth noting is that with the exponent on the outside of the brackets, everything inside the brackets is included in the repeated multiplication. So with the exponent on the outside of the brackets, everything inside the brackets is included in the repeated multiplication. So this -2 in brackets to the power of 4, that is equal to -2 times -2 times -2 times -2, because the 4 is applying to those brackets. So those brackets are in there as a factor 1, 2, 3, 4 times. In the other case, though, we would also say this out loud as -2 to the power of 4. So this out loud with our words, -2 to the power of 4. And on the right, -2 to the power of 4. But when we print it out, now we can clearly see, we remove that ambiguity, and we see that this 4 applies to something. The thing immediately to the left of it is this 2. This negative out here is kind of like saying it's -1 times 2 to the 4. And I'm going to write that right down. Okay, that arc went a little weird. Nailed it. So, the exponent here, the exponent only applies to what is immediately, my M messed up, immediately immediately next to it. You can imagine it as -1 times 2 to the power of 4 instead. Because writing it that way, first of all, makes it clear what the exponent applies to, but also we've got an order of operations going on. Good old BEDMAS or PEMDAS, whichever version you're working with in your head brains. But the exponent has to happen before multiplication. So this power of 4 happens and then multiplication by -1. And expanded, you can write this as -1 times 2 to the power of 4. And 2 to the power of 4 would, of course, be 2 times 2 times 2 times 2. We can write that a little bit more succinctly, where we have -1 times 2. We could just write that as -2. But the other ones are still just regular 2's. So, where's a nice color? So in here, 2 times 2 times 2 times 2, we have 2 to the power of 4, but we're taking the negative of that. And that's what this expression says. That sure, you've got 2 to the 4, but take the opposite of it. On the next page, there's a bunch of examples. Similar to these, you're going to write each of those examples as repeated multiplications. So 6 examples of that. After that, there's 6 examples of trying to write them as a single power. Take a moment now. You'll pause the video. You'll try these examples. You'll give them a go. And then once you're done, of course, resume. And I encourage you, because there's lots of space here, if you're really not sure, put a guess somewhere. And then if the actual answer is different, you have room for that as well. But pause the video now and resume in a little bit. And welcome back. We're going to put some answers up in this business. This 7 does not apply to -5. It applies to just the 5. That negative still exists. So this is equal to the negative of 5 to the power of 7, which will involve the number 5 as a factor 7 times. So 3, 4, 5, 6, 7. And if your answer was same as this, give yourself a way high five. Nice. And if it was different, I would say don't erase what you've got. Don't cancel it out and say that never happened. But even if you have a different color available, something, draw attention to whatever it was. If you accidentally didn't have enough 5s, well then say, hey, I need an extra 5 there, and make a little note to self that said, missed a 5. Or if you accidentally had all these as -5, then again, make a little note to self. You can say you made a little oopsie poopsie. Whoops. Should only be one negative and the rest positive because of how this exponent applies. So if that was a case for you, again, make note of it. There's no need to erase that an oopsie poops ever happened. It's not really a mistake. It's only a mistake if we don't learn from it. And by making note of what happened, we can more easily ensure that we learn and grow. My 5 looks weird. I'm going to adjust it. Nailed it. All right. Enough of my voice. Time for my voice. This 6 applies to these brackets. So the answer here is going to have the brackets 1, 2, 3, 4, 5. Oh, that's me running out of room. Should really shrink these brackets. I'll make room. It'll be fine. And 6. So that's 1, 2, 3, 4, 5, 6 of those because of the exponent of 6. And each one of them contains negative 4. Down on the left. Example C, exponent of 3 applying to some brackets. So this is equal to those brackets times those brackets times those brackets. They're in there 1, 2, 3 times. And those brackets contain a 5xy each every time. Over here, negative 9x squared. The square, well, can't apply to that brackets. That negative. That's way out there. Maybe it applies just to the 9x. But no, we don't have brackets around 9x either. This is different. That exponent of 2 only applies to the x. That's what's immediately to the left of it. If we write this like real full out, it's like negative 1 because of that negative, times 9 because of that 9, and between the 9 and the x right in there is more multiplication. So this is really what we're working with. And with that in mind, well, there's that negative 9 in front. And that's being multiplied by x squared. So times x times x. And kind of moved around on the terminology there. You heard me say to the power of 2. You heard me say squared. Exponents, when the exponent is 2, we could say that's x to the power of 2. We can also say it's x squared. And it's called that just because if we had the area of a shape with dimensions x by x, the area of that would be its length times its width, and since it would be a square, we say x squared. That one's du and done. Next one should be super easy, right? Whoa! That's got a lot of stuff going on. There is like an exponent here, there, exponents everywhere. Each one of those has their own base. So this exponent of 4 just applies to this y. The exponent of 3 just applies to this x. This exponent of 5 just applies to this 3 and not this negative because there's no brackets around here. Nice try. So writing this fully out, we have the negative of, well, there's 3 to the power of 5. I might have to write this real small. 3 times 3 times 3 times 3 times 3. There's, counting for a couple things, the negative we've accounted for, 3 to the 5 we've accounted for. Next we have x to the power of 3. And remember, there's multiplication in between between all these components. So we multiply by x times x times x. And that covers this x to the power of 3. And that's getting multiplied, the implied operation, that's getting multiplied by y to the power of 4. And y to the power of 4 is y times y times y times y. Whew, that one was a doozy. If you got that answer correct, you should, at this exact moment, give yourself a way high five. Just to be clear, to give yourself a way high five, you need to reach way above your head. Not just like sort of in front of you, but like a full-on stretch. And if you didn't get that answer, that's okay. We're like learning right now, right? There's going to be some bumps along the way. That's okay. If you got something different, keep this on your page. Don't forget. But just like point out any oopsie poopsies that happened. And if there was an oopsie poops of some sort, draw attention to it. Don't pretend it never happened. Over here, whoa, we got fractions involved, but still This exponent of 4 is just applying to some brackets. So when I say what this is equal to, it's just some brackets times some brackets times some brackets times some brackets. Those brackets 4 times. Those brackets just happen to contain whatever this fraction is, which is negative 5 over 7. Each and every time. So that is us expressing some given expressions in repeated multiplication as a form. And we can also go the other way. You tried these examples, and let's see how we did. We have something repeated. That thing being repeated is 1/2. 1/2 is the base. It is repeated 1, 2, 3, 4, 5 times. So we have to put an exponent of 5 on here. But be super careful, because if we just go like this, well, based on the order of operations, this 5 applies to this 1, and then there's division by 2. We want the 5 to apply to the entire fraction, so we have to put brackets around that entire fraction. And now that one is super correct. Over here, we've got something repeated. There's 5 and 5 and 5 and 5 and 5 and 5 and 5. I forgot to count along the way, but there's a bunch of 5s regardless. So there's a 5 involved, for sure. That's your base. That's what's getting repeated. Not negative 5. That negative is just only out in front. It's not anywhere else in any of these. Just a bunch of 5s. And how many? 1, 2, 3, 4, 5, 6, 7 of them. So it's kind of like 5 to the power of 7, except for this ding-dang-darn negative in front. So we'll put that ding-dang-darn negative in front and say now these two expressions are equal. And we keep going with it. Brackets repeated. So we're going to have those brackets to the power of 4. It just so happens that those brackets contained negative 0.5. Negative 0.5. Done. Next example. 7a is what's getting repeated again and again and again. So 7a is the base, and it gets repeated 1, 2, 3, 4, 5, 6 times. Again, be super duper careful. If we just put this 6 here, by the way we've written it, it only applies to the a. That's what's immediately next to it. The 7 is attached to the a through multiplication. That would happen after taking a to the power of 6. So if we want that exponent of 6 to apply to the whole thing, we need to put brackets around that whole thing. Down on the left, example E, we've got negative 2 times negative 2 times negative 2. And we're not going to write this. It would be equal in the end, but as a condensed power, we need to make sure we're very clear in saying that this exponent of 3 applies to this whole entire base. It's not just 2 getting repeated, it's negative 2 getting repeated. So we put that negative 2 in some brackets, say it's happening 3 times, and now those two are equal. I should line this up a little bit better. Just for where the equal sign goes, you just want to make sure it's clear what goes right before it. So it wouldn't be good form to have this like way over here somewhere. I guess it's like, okay, what's before that? Something here? Something here? No. Good form should go like right underneath or even slightly to the right. And then, last one, thing getting repeated is 6. It happens what looks like 7 times, and there's this negative in front. So we put this negative in front. And now, those are for sure equal. Other questions anyone has for me right now? I could answer them. Just kidding. I can't see your hands. Boy, did I trick you. But But enough joking around. There's another example to tackle. Cha! We have to evaluate all these expressions, and there's 5 of them. I'm going to take you through this one first, and then you can try the others for a quick bit. When we do this, when we're evaluating expressions, the biggest thing we have to adhere to is the order of operations. Again, it's that BEDMAS, as it's often remembered. Or if you prefer to say it's parentheses and not brackets, then yeah, PEMDAS. Anyways, this addition can't happen first. That's like one of the last things to ever happen in the order of operations. The exponents, they take priority. So in our heads, we can kind of think about what's happening here as this 3 to the power of 2 being 3 times 3, and this 2 to the power of 3 as being 2 times 2 times 2. But what we actually write down on our page is what those are each equal to. So first step is to evaluate those powers. 3 to the power of 2, in our heads we're thinking 3 times 3. On our paper we say that's 9. Then there's this plus sign. That would go next. And then after that is whatever 2 to the power of 3 is. And in our heads we've got 2 times 2 times 2. On paper we're writing that that's 8. And to finish this off, all we need to do is write down what 9 plus 8 is. And these days, that's 17. I dare you to try the remaining 4 examples. Be very careful about your order of operations. Be careful about what negatives apply to or what the exponent applies to when negatives are involved. But give them a go. Give them a try. Give them a shot. Give them a spin. Give them a whirl. Give them a stab. Give them a wholehearted, honest attempt. And pause this video for, what's good, like 6-7 minutes, and then resume. Well, I'm assuming you paused, and now you've resumed. Just to hear my lovely voice, or to learn math, or both. What we have here, -4 squared plus 3 cubed, can be simplified. We can evaluate that in our heads. We're looking at this -4 squared as the negative of 4 times 4. And as the negative of 4 times 4, it's the negative of 16. 3 to the power of 3, or 3 cubed. In our heads, we're thinking that's 3 times 3 times 3. So on the paper, we're writing that 3 times 3 times 3 is 27. Now that we've got it as -16 plus 27, we just need to figure out what that number is. If you want, you can think of it as 27 minus 16, because that's same. Positive 27 minus 16, same terms, just switch the order. Regardless of how you get there, we do need to get that is 11. Example to C. This is equal to something. Again, we can think about how this would look in our head brains. -2 times -2 times -2 times -2. When I evaluate that, I do it in a couple steps. First, I figure out what the magnitude of this value is. So I'm looking just at 2 times 2 times 2 times 2. And 2 times 2 times 2 times 2 is 16. But I also want to check if it's positive or negative. Because this is negative, that's negative, that's negative, negative. What happens when we multiply all those together? We know that the product of a negative and a negative is positive. We know that the product of a positive and a negative is negative. So if we multiply these two together, we get something positive. And then when we multiply that, by this next 2, we have a positive now times a negative, so that's negative. And we multiply that over with the last 2, now we're back to positive again. So this is really positive 16. Of course, we don't need to write positives in the beginning of something. Without a sign, it's assumed to be positive. And then the other component, 5 to the power of 2, or 5 squared, we're thinking that's 5 times 5. And on our paper, we just write, that's 25. And finally, we add those together to get 41. And just to repeat, like the stuff that goes on in the head brains, it does just have to be in the head brains. This is me. This is my thinking face. I have my hand on my chin. You don't have to put on your paper. If it does, it helps, or you can put on a scrap paper, because that can be useful as well. But on your actual presentation of work, all this stuff in blue, that's all you really need to show. So just be aware. Oh, I erased myself. I'm gone. Nope, I'm still here, and I'm doing example D. So we're going to zoom through these last couple. Negative 6 squared. Well, 6 squared is 36. So the negative of that is negative 36. We are subtracting 5 squared. 5 squared is 25. And then we are adding whatever negative 2 to the power of 6 is. Well, we might want to think for a quick second. So negative 2, negative 2, negative 2, negative 2, negative 2, and a negative 2. I think I got them all in there. So negative times negative is positive. Times a negative is negative. Now it's positive. Now it's negative. Now it's positive. So overall, this is a positive number. So that's done. 2 times 2 is 4. Times 2 is 8. Times 2 is 16. 16 times 2 is 32. And 32 times 2 is 64. Okay, there's 3 numbers being combined here. You can do them in any order, kind of like left to right here. Negative 36 minus 25. Well, if it's minus 36 degrees outside and it drops by 25, you're going to be really cold. It's going to be minus 61 out there. And 64 more than that will warm up to a pleasant, balmy 3 degrees, like a nice October morning. And last up, 3 cubed is 27, plus 4 cubed, negative 4 cubed. And this is negative 4 times negative 4 times negative 4. Negative times negative times negative is going to be something negative overall. And then 4 times 4 times 4. Well, 4 times 4 is 16. And then 16 times 4 is 64. Now, I wrote this as plus negative 64. If you happen to just write it as 27 minus 64, that's also legit. I just happen to write it this way to really emphasize that we still have this plus going on, and negative 4 to the power of 3 is this negative 64. So it helps just kind of trace what came from where. Totally your call, though. And then final step, of course, is just to make that combination. If it's 27 degrees out and we add a drop of 64, we're going to be at negative 37. And just like that, this lesson is done. You don't have to hear from me anymore. Thank goodness. I'm assuming there's like practice work or homework involved or something, so I guess do it, or just see what Miss T posted on Teams and try that out. Remember, powers are cool.